All right. Here we go. So here's the plan for today. We're getting into 7-2. 7-2 will take a couple days on, hopefully just 2. See how that goes. 7-3 is a 4-method section. It's a marathon. So we're going to go over a couple methods in that section, quiz on 7-2, and then the first half of 7-3, and then finish 7-3, and then have a quiz over all of 7-3. That's the plan. All right. Huh? It's only 2 sections. Well, kind of 3 sections. We already did 7-1. I looked through the Khan Academy results, and it seems like we're still struggling with some of the concepts of what the meaning. They love to ask, what is the meaning of this? And of those ones, it looks like that's what you guys struggle with the most, of like figuring out what does this represent. So my plan is to have you guys go over the FRQs tonight. Like I posted the rubric for that. I'll show you at the end. You're going to do a few homework problems from 7-2. You're going to score the FRQs with the rubric. And then we'll kind of have some time, hopefully, to, I don't know where that time's going to come from, but to get through the rest of 7-2 and go over that stuff. I definitely want to discuss where we are with that content. So that's where we're going. Now, 7-2 is called areas in the plane. That's pretty vague. Technically, we're going to be doing areas between 2 curves, or a curve and a line. I put curves in quotes there because it could be a line. It could be a curve and a line and so forth. So, quick little intro, and 4th grade did not go anywhere close to where I thought we were going, so we got off on some side topics, like mathematical conversations. We'll see where today goes with you guys. All right, so the idea for today, we have an f of x function. And based on what you wrote down, I'm not sure if you paid attention to what you wrote down or not. We know how that goes. What is the relationship between f and g? Look down to your notes. F is greater than g, meaning here's f. G, I mean, there's intervals where f is greater than g, and then there's some intervals where g is greater than f. But if we're talking about area between curves, it's probably going to be this region between f and g, where f is above g. Do we all agree with that? Make sense? Now, we know how to do this already. I bet if you didn't see the shortcut, I bet you would think, well, if I want to find that yellow area, I could couldn't I find the integral from a to b of f of x dx? And then find the integral from a to b of g of x dx? And do what with those two? Subtract, right? I mean, you find the red, area under the red, that's what integral does. The area under the blue, and if you do red minus blue, you're going to get what's between, right? I mean, it's pretty straightforward. And so you could subtract these two. And way back when we learned properties of integrals, if they have the same bounds, we could just subtract within the integrand one integral. And that's where this comes from. That's where this idea comes from. You can do f minus g, as long as f is above g. F minus g from a to b, that will give you the area between the 2 curves. Does that make sense? One note always comes up. What if they're both collectively below the x-axis? 1, will that still work? 2, what about the sine of that area? So I'm not changing this. This is still f minus g. What's the yellow area going to be? Positive, negative? What do you think? Or I don't know. I don't know. That's fine.
Negative.
Negative? Cooper?
But it has to be negative f of x plus g of x.
Okay. Time.
Would the f of x, or like if you did the integral for it, would it come out being negative? So then just be like negative minus and then smaller negative, so make it like negative minus negative plus.
These are all reasonable ways to think about it. Okay. So here's what we're going to do. I don't want to do this very much, but it's worth drawing it once, maybe more than once, and then showing you how to analyze it. Because once we get to 7.3, we're actually going to take this region, the same region, and instead of finding the area, we're going to revolve it around maybe the x-axis. We'll revolve it around another line and create volume. And so sketching in some sample segments might be useful right now. So here's what we're going to do. I'm going to draw in a segment. Now, pretend that's a rectangle. I mean, technically it is. It has width, right? And it has some height. Just pretend it's a very thin slice. We don't need to build the idea of what a Riemann sum is anymore. Riemann sum, we made the width like a half and the height, f of x, whatever it was. And we added them all up. And then we're like, okay, let's make the 1/2, a 4th, an 8th, 16th. Make it go to 0. So we're filling the area with these rectangles. Now, if you make them thin enough, they're like these little slices. Can you picture all the slices that would be here? You know, just a bunch of rectangles being drawn right next to each other and then shading in the whole area, right? Everybody good with that? So what is the length? What is the height of each one of those rectangles? Because we know the idea of calculating area is to add up all the rectangles from left to right, from A to B. We're all good with that, right? But instead of Riemann sums, we're going to have an integral. But let's go back and build it up based on rectangles. What's the height of each rectangle? F of x minus g of x. Right? F of x minus g of x is the length. And that changes. You know, that gets longer here and it gets narrower. But in general, it's defined by f of x minus g of x. Now, let's make it specific. Let's say this is a height of -3. And this is a height of -5. What is the length of this height of this rectangle? -3 minus -5, right? This one is -3 top minus bottom -5, which ends up being 2. And what are we going to do with, times the infinitely thin base, right? Get an area. How about the next rectangle over here? The height is going to be, I don't know, but it's going to be positive, isn't it? And what am I doing with all those values? Adding them up. Isn't that area going to be positive? Do you all agree with that? If you keep doing top minus bottom, because we're only going where f was greater than g, that's how they defined it. If we're always going top minus bottom, aren't we always going to get a positive area, no matter whether the region is below or above the x-axis? Does that make sense to you? So these will always result in positive areas. Let me say it again. These will always result in positive areas. If you get a negative, don't be lazy and say, oh, I must have done the wrong top and bottom function. Change the negative to a positive. No, go back, switch the top and bottom, or maybe you did a calculation wrong. Okay, it should be a warning flag for you. Top minus bottom. Top minus bottom. And how are we stacking these rectangles? From left to right. From A to B. Make sense? Top minus bottom. We're stacking them from A to B. All right. Now, let's do this next one. This one's a little different. We got cosine x, we got sine of x. We're going from 0 to pi over 4. All right. Make me proud, please. We got cosine of x, we got sine of x. Which one's the red one? Cosine of x. Do you agree? Green one? Sine of x. Find the area of the region between. So we're going from 0 to pi over 4. Where's pi over 4? Right, but on this picture, where's pi over 4? Where they intersect, right? Yes? I need you to be honest with me. How many of you did not realize that? It's okay. All right. So here's what I realized the fourth period, okay? I really need you to be honest with me. Okay? I don't want to waste your time, but I also don't want to shortchange you. You're going to college next year, and no longer will I never learned the unit circle, work on your professor, okay? Seriously. So be honest with me. Have you ever seen the relationship between the unit circle and the graphs of sine and cosine? Okay. Before we start the problem. What's up? No. I've done that for you a bunch of times. 0 radians. Ready? 1, 0. I'm only going to do a couple of these. Pi over 6. Help me out. Pi over 6. What's the x value? What's the cosine? Radical 3 over 2. That's a 3 over 2. What's the y value? Good. Pi over 4. Radical 2 over 2. Radical 2 over 2. Because the cosine of pi over 4 is radical 2 over 2. The sine of pi over 4 is radical 2 over 2. That's where they are equal. Equal, bless you. Equal, intersect. Intersect. Keep going. Yeah, that's actually enough for now. All right. Listen. The unit circle really should be taught with the graph of cosine. Do you guys know what the graph of cosine looks like? Starts at 1, goes down, crosses, goes down, back up. Okay. What's the cosine of 0? 1. What's the cosine of pi over 6? Radical 3 over 2. Okay, as a decimal, because we're looking 1, we're going down. Okay, radical 3 over 2 is a decimal. 0.87. Just trust me. It's 0.87, okay? 0.87. So 0.87. Pi over 6. Okay, let's keep going. Pi over 4. What's the cosine of pi over 4? Radical 2 over 2. As a decimal. You guys get your calculators out. You'll need them. I think it's 0.707. But 0.707. You'll need your calculators today anyway. So here's what's happening. Once you've typed that in, look up here. Okay? the cosine of pi over 4 is radical 2 over 2, or as a decimal, 0.707. What's happening to cosine as you get to pi over 2? The cosine values keep going down because the graph of cosine is going down. They're related. They're the same values. Okay? We're only finding some of them. We plugged in 0, pi over 6, pi over 4, pi over 3, pi over 2. But we know it's a continuous graph, right? There's more between them. And every output on the unit circle for cosine spits out a y value on the xy plane for cosine. So by the time you get to, okay, cosine here, what was cosine of pi over 2 again? The point there is 0, 1. What's the cosine? 0. Okay. Pi over 2. Then what does cosine do? It goes into the negatives, doesn't it? Right? The unit circle generates, or vice versa, I guess you could go either way. The cosine graph generates these values on the unit circle, and vice versa. Okay? That's where it comes from. Now let's do the same with sine. Here we go. What's the sine? We're doing y values now. What's the sine of 0? 0. Okay, look. 0, 0. What's the sine of pi over 6? 1/2. Okay, 1/2. What's the sine of pi over 4? Radical 2 over 2. Sine's going up, cosine's going down. That's where they cross. We good? Okay. Unit circle comes from the graphs, the functions, cosine x, sine of x. All right. What do we want? We want the area between the functions. Okay. So that intersection point was important. Let's draw in a sample. You don't need to do this. You're going to need to in section 7.3. Do you agree the height of that rectangle is going to be cosine x minus sine of x? Do you agree? Top minus bottom. Most of you won't need to do this right now. But if you get confused on the interval you're looking at, do top, bottom, draw in a little rectangle and say, okay, it's cosine x minus sine of x. That's going to help you as you read out the integrand. Okay? But we know we're starting at 0. Did 0 come from an intersection point? No, it was given to us, wasn't it? Okay? So in this previous problem I did, they may use the word find the area enclosed between f of x and g of x. Okay? Doesn't that imply that they cross and you have to find out where the area between the area on the interval between the intersection points? Okay? This one, we had to be told 0. They could have told us, to their first intersection point. They're not going to do that. But we can see, since I gave you the graph, we go from 0 to pi over 4. We were told that as well. 0 to pi over 4. Then your only decision is what's the top function, what's the bottom function, and we know since we're going from left to right, we're going to integrate with respect to x. That's not even a question today. Tomorrow it'll be a question. All right. Everything today is with respect to x. So what's my top function on the interval? Cosine x. What's the bottom function on the interval? Sine of x. You're going to literally type that in your calculator. It's going to give you an answer, and we're done with the problem. It's like 0.404. Huh? 414? Always to 3 decimals. 0.414. 0.414. So this chapter, we're going to use the calculators quite a bit. We did a whole chapter on antiderivatives by hand. Okay? The hope was that you mastered that. Now, as we learn new content, the calculators are going to be there to just replace that process and allow us to just think about the application of it. So could we do this by hand? What's the antiderivative of cosine of x? Sine of x. Antiderivative of negative sine of x plus cosine x plus a constant from 0 to pi over 4. We'll do this real quick in our heads just to practice. Sine of pi over 4. Radical 2 over 2 plus radical 2 over 2. Radical 2 over 2 plus radical 2 over 2 is 2 radical 2 over 2, which is just radical 2. Stick that in your mind. Minus, we're going to plug in 0. Sine of 0. 0. Plus cosine of 0. 1. Radical 2 minus 1. Radical 2 as a decimal is 1.414, I believe. Minus 1 is 0.414. So radical 2 minus 1, or 0.414. Another backup protection for you. Ready? For this one. We knew what it looked like. If I break that up into a rectangle, I know that rectangle is too much area, but it has a height of 1 and a width of pi over 4. A width of radical 2 over 2, right? Not radical 2, sorry. That's the sine of pi over 4. Pi over 4 would be like 3.14 divided by 4, about 3/4 times 1. So we know this is going to be under 3/4, which it's kind of just a ballpark to say, okay, am I close? If you want another backup for approximation reasons. All right, moving on. Find the area of the region enclosed by the parabola x squared minus 1 and y equals x plus 1. Enclosed tells you that they are going to intersect, right? Twice. How should we define the intersection points? What's up? Yeah, you could just graph it. Let's practice it by hand as well, because they will require you to do some of these by hand. And you guys tell me you don't know how to factor, so we'll go ahead and practice. Could you solve this by hand? Do you feel confident with that? X squared minus 1 equals x plus 1. What would you do first? Yep. I'd probably keep the x squared positive. So subtract the x and then subtract the 1. Yes? What does that factor into? You guys agree? X minus 2. X plus 1. We have two factors multiplied that equal 0. Set them both equal to 0. So x equals 2 and x equals negative 1. That's nice because it tells you right away your integral is going to go from negative 1 to 2. Negative 1 to 2. Now we have to decide top minus bottom. What's the easiest way to figure out other than graphing? Top minus, or which one's top, which one's bottom? Plug in a point, yeah. Let's plug in a point between negative 1 and 2. What makes sense? 0. Let's plug in 0. In the parabola, 0 squared minus 1, negative 1. In the line, 0 plus 1, 1. Which one's higher? The line. So, x plus 1 was our top function. Parentheses, x squared minus 1 was our bottom function. A quick little visual for you as well. You could probably graph this by hand pretty quickly. Doesn't x squared minus 1, isn't it a parabola that's just shifted down 1 unit? Right? And isn't y equals x plus 1 a line with a y-intercept of 1 going like that? So we've got that graph. And we can see there on there as well that the line is above the parabola. All right. This would go right in your calculator. You can do it by hand as well. You could distribute the negative, combine like terms, use the power rule. Don't forget, add 1 to the exponent, divide by the new exponent. And what'd you get for this one? Negative 1.5? 9.5? Yeah. So when you get a negative, double check your work. Did you put parentheses around both functions?
Yeah.
You guys said 9 halves? 4.5 sounds right. Questions on that? All right, next one. We're going to do this problem a couple times. We're going to do it different ways. I think we've had the conversation about y equals radical x versus y squared equals x. Yes? Here's what I would caution you about. If you're doing this with a calculator and you graph these, here's what you're going to get. And your eyes are going to be tempted to find the area here. So let's read the problem together. Find the area of the region R in the first quadrant. First quadrant. That is bounded above by radical x, below by the x-axis, and the line x minus 2. Everybody see the region we're talking about? The one I kind of put diagonal slashes. Everybody good with that? Now, what do we have to be careful about? What do we have to be careful of for this one? Yeah. So that's 1. Ready? I'm going to go the integral from what to what? From 0 to, well, let's go ahead and draw in a sample Riemann sum rectangle. Do you agree the top function is radical x? What's the bottom function? Not yet. It's not going all the way down there. It's staying in the first quadrant. So it's going from radical x down to the x-axis. What's the problem here? Or do you not see a problem?
It goes below that normally.
Normally it would go below, yeah. And then what happens right here? Top function, radical x. Bottom function, x minus 2. So if you tried to set this up with one integral, top minus bottom, do you agree you'd be finding this area all the way down to that green line? And you don't want that at first. Do you agree? Okay. So you have to actually split this up into 2 integrals. You're going to have to go from 0 to this point. What is that x value? 2. It's the x-intercept of the line, 2. Where the top function is radical x. Bottom function is, what's the bottom function? X-axis, right? What's that integral going to be? Radical x minus 0. Wait a minute. That's just a plain old integral. That's just the area under a curve, isn't it? Isn't the definition of an integral the area between the x-axis and the function? So the top and the bottom, it's just the top, right? So radical x dx plus the integral from 2 to, where do they cross? At what x value? 4. Good. Where the top function is radical x minus, be careful, parentheses around the bottom function, x minus 2. Do you see? You need to be careful on this one, or ones like this where sometimes the top and the bottom function will kind of switch. Anytime they switch, top and bottom switch, or one of the top or bottom switch, you might have to break up the integral, all right, into 2 parts or 3. All right, some of you are not clear on where they intersect. You could set x minus 2 equal to the square root of x. Square both sides. Radical x squared is x. What's x minus 2 quantity squared? X squared minus 4x plus 4. Good. Have to FOIL it out. So we have to subtract x over. So x squared minus 5x plus 4 equals 0. What does that factor into? X minus 4 times x minus 1. So my zeros are 4 and 1. That's where that 4 comes from. What about that 1, though? Do we all agree it's 4? 4 is the one we want. But just because I'm a nerd, where does that 1 come from? Yeah, but that's telling us that's where the graphs cross. That's where the green and red graphs cross. Got it?
Well, whenever you plug in 1 to the y equals x minus 2, you get negative 1. But if you plug the negative 1 into the x, like the square root of x, you can't do that.
Right. I agree. So why is it telling me they cross at 1? You're right. When you square radical x, don't you get the same thing as if you squared negative radical x? What does negative radical x look like? Remember seeing this graph? It didn't know where it came from. It's like, hey, you squared me. Okay? I'm going to give you a solution for both results, whether it was radical x squared or I don't know if it was negative radical. We knew it was positive radical x being squared because we can see it. It could have also been negative radical x being squared, and if so, they would cross again at when x is 1. Okay, that's the difference between, and I wish I had time on this. That's the difference between this and y squared equals x. Ready? Let's see if you learned what I tried to teach you this year. What's the square root of y squared? Huh? Plus or minus y. Right? Couldn't y have been negative 6? Couldn't y have been positive 6? Square root of x. Multiply the plus or minus over. Y equals plus or minus the square root of x. That's where it came from. It's like, hey, I didn't know if I was going down there or not. You just squared me. All right? I'll give you the result. That's what all I'm trying to say is be careful. When you go to solve them, make sure you're ignoring what's called the extraneous solution if it doesn't apply to the problem you're working on. All right, last one for today. Same problem. Tell me a way around this. What's that going to give me? Isn't the area under radical x going to give me all that area right there? It's too much. I need to take away what? I need to take away the area under the green part from 2 to 4. And because this is a line, you don't have to do calculus. You could treat it as a triangle and take away the area of that triangle. But if it was a curve, you don't have that choice. You have to do calculus on it. There's other options here. That's a fine way to do it. Good? All right. So tomorrow, ready? Top minus, wait a minute. Top minus bottom's not going to work tomorrow. Instead, we might have to go right minus left, and our bounds won't be from A to B. We're going to stack from, not from left to right, from bottom to top. Yeah, you're pretty much just doing it with respect to that. All right, homework for tonight. All right, homework for tonight. You're going to do those problems in the book, and then you're going to check your FRQs. The link to the rubric is right there.
You almost already did that.
Did you guys already check?
Yeah, you just found them online.
That's fine.
But when you get stuck, it also has all the work on it as well. The work doesn't always follow. The work for the second one part D, which is where you have to like do. You have to find like you take the process is called. You take the DD, DT, and on both sides, and like